Okay, today we continue the study of sets and functions, and first we introduce some set theoretic constructions. The first of which is the power set. Here's the definition. We studied about power set last week, but here's the more formal definition. First, let A be a set. Then the power set of A is the set of all subsets of A. So that, and we write this power set as P of A, or some people prefer to write 2 to the power of A. Okay, this A is a set. So don't confuse this as a number. It's not a number. But anyway, this is the power set of A is defined as elements which are subset of A. Okay, here this A, lowercase a, is a set which is actually a subset of A. Okay, and here's an example. Suppose, example, A is the set of 3 numbers, 1, 2, 3. Then the power set of A is this. Empty set consisting of only 1, only 2, only 3, and 1 and 2, and 2 and 3, and 1 and 3, and 1 and 2 and 3. So there are 1, 2, 3, 4, 5, 6, 7, 8 elements. By the way, this last element is the same as A, right? It's A itself. For any power set, we always have empty set and the original set itself as an element of the power set. Okay. And here, notice there are 8 elements, which is the power of 2 to the power of 3. And that is why we often write power set as 2 to the power of the set. And in this case, this represents the number of elements in A. So if the number A contains 2 elements, then there will be 4 elements in the power set. And if there are 100 elements in A, there will be 2 to the power of 100 elements in its power set, and so on. That's why we write like this. Okay, next set theoretic construction we define is called the Cartesian product. Cartesian product. This word, Cartesian, we usually write with a capital letter for C because it came from a proper noun. This is actually the adjective form of the proper noun Descartes. Descartes. It's called Descartes. He's a 17th century French philosopher and mathematician. I think he is most famous for saying this phrase, I think, therefore I am. This is not something, whatever this means, this is not something Billie Eilish said first. Okay, so this term Cartesian came from Descartes. So Descartes obviously defined this concept for the first time. And here's the definition. Let's say we have 2 sets, A and B. And the Cartesian product between A and B is written as A times B. A and B are not numbers, they are sets. This is defined as the set of pairs, where pairs means one element A from the set A and one element B from set B. So that is A belongs to capital A and B belongs to capital B. So this is an ordered pair. Ordered means A, B is not same as B, A. Okay, so this order, A comes first, B comes next. It has a meaning. Okay, and also if A, B, this pair is the same as C, D, then this means A is equal to C and B is equal to D. Okay, if and only if A is equal to C and B is equal to D, then this pair AB and this pair CD are equal to each other. Okay, so this is the definition of the Cartesian product between sets A and B. And now you should notice that this Cartesian product between A and B is itself a set. So if there is another set, let's say C, then we can define another Cartesian product between A times B times and C. Okay, so this will be the set of pairs where the first pair is a pair. Okay, is a pair of pairs, and the second element of the pair is an element from C. Okay, so A, B is a ordered pair defined in this Cartesian product between A and B, and C belongs to capital C. In a similar manner, we can first define the Cartesian product between B and C. Then we can define another Cartesian product like this. Okay. This is again a pair where the first of the pair is an element from A and the second of the pair is a Cartesian element of a Cartesian product between B and C. So A belongs to A and BC belongs to B times C. And strictly speaking, this Cartesian product, AB first, then C, and this Cartesian product, A times BC, they are different. They are different because look at this element. The first element of this Cartesian product is a pair, but the first element of the second Cartesian product, this one, is just an element of A. So obviously this element is different from this element, even if this A on the left hand side is the same as this A on the right hand side, and this B on the left hand side is equal to this B on the right hand side, and this C on the left hand side is equal to this C on the right hand side. Now these pairs are different. However, of course, they are more or less the same because all the elements, basic elements, A, B, C, are the same. So we usually consider them as almost equal in some sense. In exactly what sense is a little bit complicated, but yeah, we can informally just consider them, these two different sets, as nearly equal. Uh, we use a specific term for this equality. It's called, these two sets are isomorphic. Okay, isomorphic. Their forms are more or less similar. Iso means same, morphic means shape or forms. So they are mostly of the same form, so we call them isomorphic to each other, and consequently we usually write A times B times C, just ignoring these parentheses. Okay, so this is more or less the same as AB times then C, or A times BC. Okay, so we can more or less safely ignore the order of multiplications between sets. And we can continue this indefinitely. So we can define Cartesian products of four sets. Of course, A, B, C, D. They are all sets, and so on. So if we write like this, then we write elements like this, A, B, C, without any parentheses inside a pair. Okay. Again, be careful. Strictly speaking, these three sets are all different, and this one, A times B times C, is just a shorthand for either this or this. Okay, there is a difference between this and this, but we may ignore for most of the time the difference, so that we write like this. We can define a Cartesian product of the same sets. For example, if A is a set, we can define the Cartesian product between A and A. So in this case, it's a pair where A and B both belong to the same set A. And we can continue this indefinitely. A times A times A times A times A times A, and so on. Since this is very common, we write like this. So in this case, A times A is written as A to the power of 2, like A squared, and A cubed, and A to the power of 4, and so on. So if we take the Cartesian product of A n times, so if there are n times, then we write A to the power of n. Okay, in this case, the elements are the ordered tuple, n tuple. Let's say when there are too many elements, it's more convenient to write like this: A1, A2, and so on up to AN. And each AI belong to A, where I is 1, 2, up to N. Okay? And I think you already know a few examples of these Cartesian powers. Cartesian powers. For example, we used A for describing any general sets, and let's say we have a specific set, the set of real numbers. Okay, so real numbers squared is a Cartesian product between real numbers and real numbers. So that is the set of pairs of real numbers like x and y, where x and y are real numbers. Okay, so this is the set by which we describe a two-dimensional plane like this. So any points on this plane, xy plane, is an element of this set, r squared. And you can similarly define r cubed, which is the set of triple of real numbers. So we use this set to describe points within three-dimensional space, and so on. Now we change our topic a little bit. Previously we introduced the language of propositional logic, right? Propositional logic. Or sometimes we call it propositional calculus. But now consider this kind of proposition. For all x in the set of integers, there exists y, which is an element of integers, such that x is less than y. Okay, consider this phrase. This looks like a proposition because it can be, either true or false, right? For any integers, there is another integer such that that another integer y is greater than the first integer. You can. This means basically, for any integer, we can find another integer that is greater than that, right? So this is something like a proposition, but we have something new here. That is this phrase, for all, and there exists. And also this x and y, they are not concrete integers, but rather they are variables that represent some integers. Okay? So this kind of phrase cannot be expressed within the framework of propositional logic. So we need something more, and that is called first order logic. For describing mathematical facts, we need at least first order logic. Okay, so now we want to define something to describe some logical operators to describe these kind of phrases. For all, and there exists, or they exist. And that is not so difficult. And for all, we write something like this. So this means for all or any x that is an element of integers, and for there exists, we write like this. Let's say y. So there exists y in integer. Okay, this symbol is kind of inverse of all. A, right? So A, this represents all or any. Okay, so if you rotate this 180 degrees, you get this symbol. And this one is a symbol for E, exists. E, okay? If you rotate this, you get this symbol. So using these new notations, we can express this phrase like this. For all x in Z, there exists y in Z such that x is less than y. Okay, so English translation of this phrase is this. Or logical translation of this English phrase is this, and vice versa. Okay? Now, you should be careful that this x here, x and y here, they are not concrete numbers, but they are variables that represent some numbers. Oh, sorry, I shouldn't write z like this. It's a set of integers. So that means if we put some numbers here from integers x and y, then this proposition can be either true or false. But here we are saying for any x, for all x, there exists y such that this proposition holds. Okay, so this proposition per se doesn't mean anything. There is a context here. Okay, so if you ignore this part, then by itself x less than y doesn't mean anything. Okay, we need this context. And be careful, this context depends on the order how these symbols for all and there exist appear in this sentence. Okay, for example, this sentence is different from this sentence. There exists y in Z such that for all x in Z, there exists x less than y. So this sentence is different from this sentence. They are not equal. Okay. So if you think about the first sentence, it looks okay. But what about this? There exists y integer such that for all x, x is less than y. So this means if you think this is too abstract, let's say, it says there exists y. So okay, let's see. So this means there is a y such that for all x, that y is greater than x. Okay, so this essentially means there is a maximum integer, right? Maximum value for integer, right? Because any integer here, for all integer, y is greater than that, right? So this doesn't make sense. There is no such thing as the maximum integer in the set of integers. So this statement is clearly false. But the first sentence is clearly true, because for any integers, there is another integer that is greater than that, right? So if you pick any integer, you can always find a greater integer. So the first sentence is true, but the second sentence is not true. So be careful about the order. You need to learn how to compose a mathematical sentence. Okay. Anyway, this symbol is called universal quantifier. Universal quantifier. And this symbol is called existential quantifier. In some cases, there can be multiple elements that is bound by these quantifiers. So in that case, this existential quantifier should read there are, or instead of there is, or there exists. You already know what negation is. So let's say if P is a proposition, then not P is denoted as this, right? So let's say if x is less than y is a proposition, then negating it means what? This is equivalent to x is greater than or equal to y. Okay, so not x less than y means x is greater than or equal to y. Okay, and so what happens if we combine negation and quantifiers? So suppose we have a proposition for all x, some proposition holds. Okay, then if you negate it, what we have is this. This is equivalent to there exists some x such that not P is true. Okay, so this negation operator comes inside, and this universal quantifier becomes existential quantifier. Okay, and similarly, if we have this proposition, there is some x such that proposition P holds. If we negate it, then this is equivalent to for all x, not P is true. Okay, so again, this negation comes inside, right before the proposition P, and this existential quantifier becomes universal quantifier. Okay, so what does it mean? So let's see. First consider this example. So for all x, P holds. So if we negate this, what this means, okay, maybe we should write for all x, P holds. Okay, so this is what this means. And if you negate it, this means obviously not for all x, P holds. It means not for all x, P holds. That means there for some x, P does not hold. Okay, so this means this. There is at least one x such that P does not hold. P is not true. So this means, so for some x, this means there exists. In other words, there exists x such that p does not hold. Which translates as there is some x such that not p is true. Okay, p does not hold means not p is true, not p holds, right? P does not hold means not p holds. So for some x, not p is true. So therefore, this statement is equivalent to this statement. And you should also try to reason how negation of existential quantifier becomes this. So try to explain how this happens. Now consider a little bit more concrete example. So our favorite example is this. For all x in integer, there exists some y, which is an integer, such that x is less than y. Okay, so we know this is true. Let's try to negate this. How do we do this? To negate this, we consider in this way. First, we have this. This acts on all of this. Okay. So first, we apply our rule. So this is equivalent to, we replace for all with there exists, and we apply this negation inside everything here. Okay, not there exists y in z, x less than y. Now we work on this part. So according to the rule, so this one doesn't change, we change this existential quantifier to universal quantifier, then move this negation operator inside this part. So that will be x, not x less than y. Now we apply this negation to this statement, which is common sense transformation, I guess. So not x less than y is x greater than or equal to y, right? So after all, this statement is equivalent to this statement. Of course, since we know the original statement is true, then its negation should be false, right? Okay. And let's try another example. Let's say there exists y integer such that for all x in integer such that x is less than y. Well, we've seen that this is false. So try to negate this. Okay, so according to the rule, first we replace this existential quantifier to universal quantifier and move this negation to inside. So that will be negation of this for all x in z, x less than y. Okay. Then again, apply the rule to this part. This part. So that is equivalent to, so we replace this universal quantifier to existential quantifier and move this negation operator inside. Okay, and we expand this negation operator by taking the meaning of this mathematical relation. The existential quantifier, and not x less than y means x is greater than or equal to y. Okay, and since we know that this original statement is false, its negation, the resulting expression here, should be true. Right? And think about it. For any integers, there is another integer that is greater than or equal to the first integer, which is true. Oh, by the way, we use y here and x here, but these are just variables, so these particular symbols do not mean anything. So we could replace with any other symbols. For example, we instead of y we could use x, and instead of x we could use y, and replace x with y and y with x, and we still have the same meaning here. So this statement is equivalent to this statement, so they mean the same thing. Of course, you could use some other symbols, like for example, you could use a and b and b and a, or you could use whatever, you could use Greek letters, Arabic letters, whatever, but they still mean the same thing because they are just bound variables. They are bound to this context. So as long as the context is clear, how they are expressed in terms of symbols doesn't matter much. Of course, you should not use same symbols for a and b or x and y. Otherwise, it's confusing. Okay. And one more thing. Any proposition about members of the empty set is always true. For example, for all x, which is an element of an empty set, of the empty set, x is a fish. This is always true, because there is no such thing as elements of empty set. So the premise is wrong already, it's false. So based on a wrong premise, anything can be true. So this is true. And so is this. For all x in the empty set, x is not a fish. This is also true. This is true, and this is not. This is also true. Because these are statements about empty sets, statements about elements of the empty set. So they are always true. Now let's move on to maps, mappings, and functions. We use these three terms interchangeably. We sometimes call a function a map or mappings, and so on. So what we want to do is to study something, and when we want to study something, mathematically speaking, of course, we define a set of our objects. Okay, suppose we have a set like set of integers or real numbers. If we want to study something, we have to define it as a set. Okay, So that defines our universe of interest. But when we want to know the properties of a set, it is often useful to compare with another set. Okay, by comparing two sets, we understand deeper about our objects. Just so, how do we compare these two sets? That one way is to define a function between these two sets. Okay, that's what we mean by compare two sets. Okay, so let's say A and B are sets. Then we define some rule to make correspondence between elements of A and B. Okay, so pick one element from A, and for each element we define a corresponding element in B. So if we define this rule for every element in A, then that defines a function from A to B. Let's call this function f. Okay, so f is a function from set A to set B. For each element of A, there corresponds an element of B. So this rule is called a function. Okay. Okay, let's see an example. We can define a function from the set of integers to the set of natural numbers by defining the rule like this. F of x is equal to 1 plus x squared, where x is an element of the set of integers. Okay, so for all element of z integers, we define this, and we can see that f of x, if x is an integer, then it is a natural number, right? Because x squared is a positive number. Since x is an integer, x squared is a positive integer. Adding that to 1 gives another natural number. So positive integer is a natural number, right? So f of x is an element of the set of natural numbers. For this, we write as a rule. So f x maps to 1 plus x squared. And this belongs to integer, and this belongs to the natural numbers. Most specifically, let's say if we choose -1, which is an integer, then this maps to 1 plus -1 squared, that is 2, which is a natural number. If we choose, for example, 3, which is an integer, this maps to 1 plus 3 squared, which is 10, and it's of course a natural number, and so on. Let us define some terminologies. Definition of domain and codomain. Okay, suppose we have a function from A to B. Then in this case, A is called the domain of f, the function f, and B is the codomain of function f. So sometimes we write dom f is A, and codomain of f is B. Okay? And by the way, function we sometimes write like this: a to b and f is here. Okay, either way is okay. This is okay and this is okay. And let us define another specific function, one specific function, which is identity function. So for any set, the mapping or the function id a from a to a, a is a set, so the codomain can be also the same set. So there is a special function called identity map. Say identity map that is defined by this. For each element of A, we define IDA of X as X itself. Okay, so it doesn't move anything. So it looks like this. We have A, and every element is mapped into itself. So that is, this looks very trivial, but sometimes it comes very handy. So this can be this identity map can be defined for any set. So in the case where A is a natural number, is the set of natural numbers, we define ID natural number X as X. So every natural number is mapped into itself. So for example, IDN 1 is 1, IDN 2 is 2, and so on. It's quite trivial. There are various ways to define a function. For example, we can also define a function with cases, which means, for example, let us define a function from real numbers to the set of two integers, 0 and 1. Okay, this is a set consisting of just two integers, 0 and 1. Okay, so let us define this function as this. F of x, x is a real number, is 1 if x is a rational number. Otherwise, it's 0. So otherwise, in this case, means if x is irrational, then the value of f of x is 0. Okay? So this is a function, because for every real number, we have a corresponding element of the codomain, either 1 or 0. Now here's another technical term called image definition. Image. Okay, suppose f is a function from set A to set B. Then the image of f, so image of f is written as Im of f, which is a set that is f of a, where a is a. Okay, so this image is the set of all elements of B that has a corresponding element in A via the function f. Okay, so maybe I should draw a picture here. We have A and B, they are sets, and for every element of A, we have a corresponding element in B, right? But it does not mean that all elements of B have some corresponding elements in A, right? Because some elements of B is not mapped from A. Okay, so let's write this as this. So entirety of A is mapped to a subset of B. Okay, so this subset is called the image of F, and that is Im of F. Okay, there can be some elements in B to which no element from A uh, come. Okay, so clearly image of F is a subset of the codomain of F. For a map from A to B, we say that image of F is a subset of codomain of F, which is B. But in the case where this is equal, instead of just a proper subset, then we say if image of F is equal to its codomain, then F is onto or surjective or a surjection, if you prefer the noun surjection, or epic. We have many terms for this, but and actually they do have some nuances, but at this point you don't have to worry too much about the difference, but we just use these terms interchangeably. Okay, so this means if we have a map A, B, and so if we have a map function from A to B, then the image of F covers entire B. So this case is this. Okay, so if this is the case, then this function F is called onto or surjective or epic. More logically, this situation is expressed as this. For every element in B, which is actually a codomain of F, there exists some x in A such that y is equal to f of x. Okay, so since the image of F covers entire B, whichever element you pick from B, there is a corresponding element in A such that this holds. Okay, so if we pick any y from B, there is always some x in A such that f of x is equal to y. So this situation is expressed as this notion, by these notions, onto surjective epic. Okay, let's see one example. We define a function from integers to natural numbers that maps each integer x into 1 plus x squared, which is a natural number. Is this surjective? Actually, the answer is no, it's not surjective. In the initial version of my lecture notes, I said this is surjective, but that is wrong. So to see this, let's pick 3, which is a natural number. So if this function is surjective, then there should be x such that 1 plus x squared is equal to 3, right? So if this is the case, then x squared is 2, so x is plus minus square root of 2, which is not a natural number. So in this case, we have the set of integers, set of natural numbers, and 3 is outside of the image of f. And there are many such numbers like this. So this function is not surjective. When we define a function from set A to set B, we should define the rule to correspond every element in A to some element in B, right? But it is entirely possible that two different elements in A correspond to the same element in B. Okay, in some cases we want to distinguish this case with the case where every different element in A always correspond to different elements in B. Okay, this case is called such a function is called to be one-to-one, or sometimes 1-1, or injective, or in the noun form it's injection, or monic or mono, noun form. We use these terms interchangeably. We usually use injection or injective. Okay. So here's a more formal definition. If is injective, if and only if for all two elements in if A is not equal to A prime, then f of A is not equal to f of A prime. If this holds, then we say the function, actually f from A to B, is injective, or one-to-one, or monic, and so on. Okay. Now, note this notion. Note this notion. If A and A prime are not equal, then f of A is not equal to f of A prime. Okay. If you take the contrapositive of this statement, this means the contrapositive. Okay, contrapositive. Meaning the negation of the right hand side implies the negation of the left hand side. Okay, contrapositive of this statement is this. If f of A is equal to f of A prime, this implies A is equal to A prime. Okay? So, in terms of this diagram, if A and A prime are different points, then they necessarily map to different points in B. Or in case if they are actually equal, then that implies A and A prime are actually equal. So that's the definition of injection. Okay, note that the notions of surjection and injection, they're different. Surjection means the map covers entire codomain, And injection means two different elements maps to two different elements in B, in codomain. So it is possible that a function is injection but not surjection, or it can be surjection or but not injection. Okay, so the image may be just a subset of B in for an injection. But yet some function may be both surjection and injection at the same time. If that's the case, it is called bijection, bijective or bijection. Or maybe iso, meaning this function maps one set to another set, and those sets are in a sense more or less equivalent of the same form, because every element, so bijection means every element of A maps to a different element in B than other elements, and every element of B has a corresponding element in A. So it is one to one and onto. In other words, it's injective at the same time as surjective. So if this is the case, the set A and B are more or less the same thing. It may look different, but essentially, at least in terms of the number of elements, they must be equal. So that's bijection. Next, we define a way to combine two functions. So suppose we have two functions, f from a to b and g from b to c. So we have three sets, a, b, c. So if we map one element from a to b, then this element in b may be mapped into some element in c. So in this way, we can define a map from A to C. So here's the definition. So we define the composition. We can compose composition of functions g after f, which this is a function from A to C. Okay, and that is defined by this x g of f of x, where x is an element of A and g of f of x is an element of C. So this defines the function composition. More diagrammatically, we may express this composition as this: A, B, so that is a mapping from A to B and B to C. That maps, this map is G, and from A to C, first we apply F, then apply G. So that is G circle F. We usually call it G after F. Okay, so F then G. That is G after F. That is the function composition. And of course, in order for this definition to be meaningful, that we require that the codomain of F, which is B, is equal to the domain of G, which is also B, of course. Otherwise, this composition doesn't make sense. Okay, so we require that the codomain of F is equal to domain of G. By the way, this g after f is sometimes expressed as f then g. In particular, in computer science, maybe they prefer to use this notation rather than this, but they mean the same thing. Let, let's see an example of function composition. Suppose we have the two integers to integer defined by f of x equal to x minus 1 and g integers to a natural number plus 0. Okay, and g of x is defined as x squared. Okay, then g after f is a function from integers to natural number and 0 defined by this. So that is g of f of x. So that is g of, first apply f and then apply g. So that is x minus 1 squared. So therefore g after f of x is x minus 1 squared. This is the composition of f and g. So far we have given a series of definitions regarding functions and mappings. Now that we have all the important notions, let us now prove some interesting properties of functions, general properties. Okay, so here's a proposition. And let f and g be functions, f from a to b and g from b to c. So these are functions. And 1, if f and g are injective, then g after f is also injective. And 2, if f and g are surjective, then g after f is also surjective. So let us prove this. First part. So suppose f and g are injective. Okay, then this means if a and a prime are elements of set A and a is not equal to a prime, then f of a is not equal to f of a prime, because f is assumed to be injective, right? Now, if this is the case, so f of a is not equal to f of a prime, then this means since g is injective, g of f of a is not equal to g of f of a prime, right? But this means, by the definition of function composition, g of f of a means g after f of a, and g of f of a prime means g after f of a prime. Okay, so this indicates, after all, this indicates if a is not equal to a prime, then it implies that g after f of a is not equal to g after f of a prime. So after all, we have this implication. If a is not equal to a prime, then g after f of a is not equal to g after f of a prime. Therefore, g after f is injective. Okay? And you can prove the second part in a similar manner. So suppose f and g are surjective. So what does it mean? First, start from g. Okay? So that means every element C in C, for every element in C, there exists an element in B such that C is equal to G of B, right? Because G is surjective. So that's the definition of surjection. Now, let's say wait a minute. Yes. So for this, for every G of B in B, oh, wait a minute. For every, sorry, it's not G of B. For every B in B, there exists some element in A such that B is equal to f of A, because A is a surjection. Right? So if we combine these two statements, this leads to, for every element in C, there exists an element in A such that C is equal to G of f of A. Right? This B can be this B. But this means C is equal to G after f of A. So after all, for every element in C, there is an element in A such that this holds. Therefore, G after f is surject. G after f, let's say, that is a mapping from A to C, is surjective. Done. As a corollary to this proposition, we have this result. The composition of two bijections is a bijection. So that means if f from A to B and G from B to C, if they are both bijections, then G after f is also a bijection. So this follows immediately from the previous proposition. Next, we prove the associativity of function compositions. That is this theorem. So let's say f is a function from set A to set B, and g is a function from set B to set C, and h is yet another function from C to D. Then we have this h after g after f is equal to h after g after f. Okay, so this means function composition is associative. Note the places of these parentheses. Okay, more diagrammatically, we can write like this. So A to B and to C to D. So we have functions A, F, and G and H. So first we compose F, then G. Okay, so G after F. Then we can compose H. So that is this part. Okay. Alternatively, we first compose G and H. So that is this. So that is H after G. Then we compose this after F. So that is, okay, maybe I should write like this. This corresponds to this, and this path corresponds to this. Okay, so either way we have the same function. Okay, so this equal sign means they are actually the same function. The order of composition doesn't matter. So this property is called associativity. TVT. Okay, this looks quite common sense, but it's something that needs to be proved. Okay, but proving this is not so difficult. We just need to apply the definitions. Okay, so for any x in A, first apply, let's see, this function left hand side. So that is G, H after G after F. So this is a function, and that applies to X. And by the definition, first consider H after G as one function. Okay, so applying the definition, we have Hg of f of x. Okay. Then we apply the function composition and the definition of function composition to this part. Okay, then that is h of g of everything here, f of x. Okay. So this is one thing. Then try the right hand side now. On the other hand, we have h of g of f of x. So consider this part as one function. So by applying the definition of function composition of this part, we have h of g after f of x, right? Then apply the definition of function composition to this part. That is h of g of f of x. Either way, we have the same result here and here. That is h of g of f of x, h of g of f of x. So they are the same. And the proof is done. Well, based on this associativity of function compositions, we can develop a whole field of algebra of function composition, so to speak, and that is called category theory. You see, this function composition just looks like some kind of addition or multiplication of functions, right? In some sense. So you can develop an entire field called category theory, and that is very fascinating. But unfortunately, we don't have time for this. But if you're interested, please do explore. I think you already know what a graph of a function is. For example, if we have a function like this, x squared minus 1, the graph, and x is a real number, graph it's something like this. So that is how does it look like? Maybe like this. And this is minus 1, and I think this is plus 1 and minus 1. This is origin. So this is y equal to f of x. So this is the graph of this function. But we want to define this more precisely in mathematical terms. So here's our first try of definition of graph. So suppose f is a mapping, is a function from set A to set B. Then the graph of f is defined to be this set A, B, where A is in A and B is f of A, which is a subset of this Cartesian product between A and B. Okay, let's see, this is A. So the graph of a function f from A to B is the set of pairs of elements from A and B. Of course, this B belongs to set B, right? So it's a subset of this Cartesian product. So according to this definition of a graph, you should note the following. First, for any A, which is an element of set A, there exists some element of B such that this pair belongs to the graph of f. Okay. And second property is that if these pairs A and B and A and B prime, if these two pairs belong to the graph of f, then that means B is equal to B prime, right? Because f is a mapping, and if the argument of that function is the same, these are both A and A, then the output of the function should be the same. So if they are B and B prime, they must be equal. So actually these are derived from the properties of functions in general. So following this argument, we define the graph of a function for the second time. Graph. Definition of a graph. Second take. Okay, so let A and B be sets, and S be a subset of A times B, Cartesian product of A and B. Then this subset S is a graph, is defined to be a graph if it satisfies the following properties. 1. For any A, any element of A, there exists an element of B such that, let's say such that A, B, this pair belongs to S. And 2, if A, B and A, B prime are elements of graph, elements of S, then this implies B is equal to B prime. Okay, if these two conditions are met, these are conditions for this subset S, then we say this S is a graph. Okay, you should be careful. There's no mention about functions here. No, we just assume there are two sets and one subset of A times B, and there's no notion of a function here. So we define the notion of graph without the notion of a function. Okay, this is important. So we are reversing the argument now. In the first definition, we assumed there was a function, then define the graph. Okay, now we define a graph without using the notion of function. So forget about functions. Still, we can define a graph in some sense. Okay. Okay, now based on this second definition of graph, we define the notion of a function again more precisely. So let's see. Definition of function or mapping. Okay, and that is, let's say A and B are sets, and S is a subset of A and A times B and is a graph in the sense of the previous definition. Okay, S is a graph. Then this means for every element of A, there is a unique element of B. So actually this is not just there exists, but it means uniquely. So in this case, we sometimes write existential quantifier and exclamation mark. Unique existence. Unique element B such that A, B is an element of S. Okay. How do we know it's unique? It's actually based on the definition here. You see the second property. If AB and AB prime are both elements of the graph S, then B and B prime are equal. So this means if there is an element with specific A, then the second element must be unique. That is the uniqueness assumption property. So yeah, this is the property of the graph. By this rule of making correspondence between A and B, we can define a function induced by the graph S. Okay. So this B, so this unique B is written as fs of a. No, this function is induced by s, the graph s. Then we write function fs from a to b. Okay, so let's examine what this means. So we have two sets, a and b, and we have a subset of the Cartesian product a times b. And if this S is a graph in the sense of this definition, then for each element of A, we have a corresponding unique element in B. So this rule of correspondence from A to B is written as this. B is equal to Fs of A. And this Fs is called a function or mapping from A to B, induced by this graph S. Okay. Now let's prove one proposition. Let alpha from x to y be a mapping or function. So this means alpha is a function and x and y are sets. Okay, then the following two statements are equivalent. F is bijective. And two, there exists a function from y to x such that beta after alpha is identity mapping of x, and alpha after beta is the identity mapping of y. Okay, so this proposition claims that these two conditions are equivalent. Equivalent means this: if one is true, then two is true, and vice versa, meaning if two is true, then one is true. So that is if one holds, if and only if two holds. Okay, so to prove this, we first assume 1, then derive 2, and then we assume 2 and derive 1. Okay, now here you should appreciate the power of abstraction. Okay, we don't care what kinds of sets are x and y. We don't care what kind of function this alpha is precisely, right? As long as it is bijective, we can conclude that there is some mapping from y to x such that these are identity functions, and vice versa. As long as we can find this function from y to x such that this holds, then we can conclude that alpha is bijective, right? We don't care what exactly beta is or alpha is. Okay, now let's prove this. First, we prove this direction. Assuming alpha is bijective, we prove that the existence of function beta such that these two conditions hold. Okay, so suppose alpha is bijective. So bijective means it's both surjective and injective. Okay, so that means for every element of y, there exists unique element in x such that y is equal to alpha of x, right? It's unique element because it's injective. So every element y comes from exactly one element in x because of so every element, so this part is due to surjection, and this part uniqueness comes from originates from injection. Okay, so this is what this means. Okay, alpha is bijective. Now, using this x, we define a function beta of y as x. So this x is the unique x that is defined by alpha. Okay. Of course, this beta is defined for every y, every element of y. Therefore, this beta is a function. Okay. And let's see, beta y is since this y is equal to alpha of x, which is beta after alpha of x. So this is x, right, by definition of beta. That means beta after alpha is the identity map of x. Okay, and now consider alpha of x, and this x is expressed as beta of y, right? So alpha beta y. So this is alpha after beta of y. But this is, alpha of x is y by the definition. So this y and this y is the same one. So therefore, alpha after beta is the identity map of y. So the first part, therefore, if we assume alpha is a bijection, then there is a function beta that satisfies certain properties. Okay, so this is done. Next, we need to prove the converse. If we assume there exists a function beta from y to x such that beta after alpha is identity of x and alpha after beta is the identity of y, then alpha is bijection. So we need to prove this. So how do we do that? Suppose such beta exists. Such means this. Okay, beta satisfying these two equations exists. Okay, so then for every element of y, we have, let's see, for every element of y, we have alpha beta y identity of y called y. So and okay, so this is of course alpha of beta of y. So this is within the image of alpha. Okay, So for every element of y, okay, consider this, x and y, every element of y, that is an element of, every element of y is an element of image of alpha because of this. So that means alpha is surjective. Okay, therefore alpha is surjective. Then in order to prove that alpha is a bijection, then we need to also prove that alpha is injective. So how do we do that? And suppose x and x prime are elements of x, and alpha of x is equal to alpha of x prime. Okay. Then we apply beta on the both sides. So beta alpha of x is equal to beta alpha of x prime. But this is beta after alpha of x and beta alpha of x prime. But this is identity, right? By assumption. We're assuming this holds. This holds. Okay. So identity of x and identity of x prime. But since this is identity, this is just x. And this is just x prime. Therefore, if we assume alpha of x is equal to alpha of x prime, then it follows that x is equal to x prime. So alpha of x prime implies x equal to x prime. Therefore, alpha is injective. So alpha is surjective and also injective. Therefore, alpha is bijective. So that concludes the proof. So now we know that if alpha is a bijection, let's see, alpha is a bijective, then there is some function in the opposite direction, such that beta after alpha is the identity of x and alpha after beta is the identity of y. So this beta is called the inverse. Actually, we can show that such a beta, such a function satisfying these conditions is unique, and it's called the inverse of alpha. And we usually write inverse of alpha as alpha inverse, like this. It's an inverse function. Okay. So if we start from some element in x, map it by alpha, and we reach to some element y, and then map this element y by alpha inverse, then we go back to the original element. And it applies the same if we start from y, any y here. We map by alpha inverse, then map by alpha, where we come back to the same element. So that's the inverse function. So, so the existence of the inverse function is equivalent to that the original function is a bijection. Now we know sets. Sets are used for defining our objects of interest under investigation. And we know functions. or mappings, which are used for studying sets, comparing two sets or more sets. Then we now define relations. Okay, what are relations? You already know some examples of relations, such as equality, or less than, or subset, and so on. Usually we define relations on a particular set. For example, this relation, less than, is defined on the set of real numbers, for example. Or it could be the set of natural numbers or integers or whatever. So this relation is something like 1.3 is less than 5.2. So this is a relation defined on the set of real numbers, or rational numbers, or integers, or rational numbers. And also, this is a subset relation. We could use something like the set of consisting of an integer 1 is a subset of the set consisting of 1, 2, 3, and so on. So this is a relation, and this is a relation. And for more general relations, we usually use this symbol. Okay. In general, if we want to deal with relations, we just use this as a relation. So A is related to B, something like that. So this tilde could be something like less than, or subset, or maybe equal, or less than or equal, greater than equal, or whatever. This symbol has no particular meaning, so we could use any other symbols like diamonds, or we could use something like this, or we could use something like this, or we could use something like some alphabets. Okay, it could be anything, but just for simplification, we usually use this tilde as a general symbol for a relation, some kind of relation. Now, we want to define relation in a more general terms. So here's the definition. Relation. So a relation R is a relation on a set S. So S is a set, R is a relation. And R is a relation, and which is defined as a subset of S times S, Cartesian product of S with itself. So this is it. It's the relation. So since this is a Cartesian product, its elements are something like this. A and B are elements of S, right? So if A and B belong to this relation, which is a subset of this Cartesian product, then we write A is related to B. Okay, so this R is the same as this R. Okay, so here's one possibly confusing example. So here's an example. Let us define a relation called equal on the set of natural numbers. Okay, so this is a subset This is a subset of the Cartesian product between natural number and natural number. So this is something like this. Ordered pairs of natural numbers. A and B are natural numbers. So how do we define this subset? So this relation is defined. Okay, so this equality is different from this equality. Okay, we are using the same symbol for different meanings, so it's confusing a little bit. But anyway, this relation is defined as this. So since it's a subset of this Cartesian product, this relation should also be a set of pairs of natural numbers. Okay, so in this case, this relation is defined as the set of pairs of natural numbers where each pair contains the same natural number, okay, A and A. In general, these pairs are something like A and B can be different. But in this subset, these the two numbers in a pair must be identical. Okay, so this is the definition of equal. So for example, 1 and 1 is an element of this equal subset, right? This relation. So in this case, we write 1 is equal to 1. Okay, so this equal is same as this equal. So of course we usually don't include these quotes, so we just write 1 is equal to 1. And 2, 3, it is not an element of this equal. Therefore, in this case, we write 2 is not equal to 3. Okay, but we have 3, 3 as an element of this equal subset, so we write 3 is equal to 3, and so on. So that's an example. As a next example, let's consider the relation less than on the set of integers. So how do we define this this relation as a subset of the Cartesian product of integers? So here's how. This is defined as a set of pairs where A and B are integers and there exists some natural number C such that A plus C is equal to B. Okay, so if A and B are integers and if there is some natural number C such that A plus C is equal to B, this means A is less than B, right? Because if we add a positive integer to A, then we have B. So this means there is some difference, positive difference between A and B, and A is smaller than B. So that's what this means. This less than relation means. So of course this is a subset of the Cartesian product of Z times Z, which is of course Z squared. So let's see. So if we have 1 and 2, is this an element of this less than operation, less than relation? Yes, because if we add 1 to 1, we have 2. So this corresponds to C, right? Therefore, 1, 2 belongs to this subset. Therefore, we write 1 is less than 2. And similarly, 3 and 8. Does this belong to this subset? Yes, because 3 times 5 is equal to 8. So this 5 now corresponds to this C, right? Therefore, 3 is less than 8. But what about 5, 5? It does not belong to this relation. Okay, therefore, 5 is not less than 8. Okay. As you can see in these examples, relations are nothing but sets. So yeah, it's not nice thing about this way of defining relations. They are just subsets of some Cartesian products. Actually, this way of defining relations is very important in database systems. So if you're studying computer science, it may be helpful to get familiar with this kind of relations. Okay. There are many kinds of relations, but among them, there is a class of relations that are of high importance. That is equivalence relations. Okay, so suppose this tilde is a relation on a set S. Okay, and this is said to be an equivalence relation. Equivalence relation. If it satisfies the following properties. First one is called reflexivity. That is, A is related to A for all A in S. Okay, maybe I should write like this. For all elements in S, A is related to itself. Okay. Second is symmetry. Symmetry. So for all elements A and B in S, if A is related to B, then B is related to A. Okay, so they are symmetric. So if A is related to B, then B is related to A. Okay, and the third condition is transitivity. That is, for all elements A, B, C in S, then if A is related to B and B is related to C, then A is related to C. Okay, so this relationship kind of transits B from A to B to C. Okay, so if this relation satisfies all these three conditions, it is called an equivalence relation. Now let's see what's equivalence relations and what are not equivalence relations. First of all, usual equality on, let's say, integers. This is an equivalence relation because for every integer we have A is equal to A. It's obvious. And two, for any two integers, if A is equal to B, then B is equal to A. Yeah, that's pretty obvious. And three, for any three integers, if a is equal to b and b is equal to c, then of course a is equal to c. Therefore, this equality on integers is an equivalence relation. Actually, it's not just on integers. It can be on rational numbers, natural numbers, real numbers, complex numbers, any numbers. Okay. What about subset relation? So this subset relation is defined on a set of sets, right? Okay. Is that an equivalence relation? Let's see. We should define this on some set. Let's say some power set of A. Okay. So we define this subset relation on a power set of some set A. Okay. So let's see, if x and y are subsets of A, then we can define whether x is a subset of y or not. Okay. Let's see. For all subset A, it's a little bit confusing. Let's use another symbol. B subset of B. Then B is a subset of itself. That's true. And what about this? If B and C are subsets of A, then if B is a subset of C, then is C a subset of B? Maybe not. It's not necessarily the case. So this does not hold. Therefore, this relationship is not an equivalence relation. And let's see. Another relation, less than, on the set of integers. This is not an equivalence relation, obviously, because, of course, A less than B does not imply B less than A. So it's not symmetric. Therefore, it is not an equivalence relation. And of course, it's not reflexive either. So, A is not less than A, right? So the first condition doesn't hold, and second condition doesn't hold, but actually third condition does hold. If A is less than B and B is less than C, then A is less than C. So this is okay. But anyway, it's not an equivalence relation. Now let's study a little bit less trivial relation. So let's define a relation, and the equivalence relation, on integers. So how we define this? This is how we would define this. So A and B are integers. A is related to B if and only if A minus B is divisible by 3. In other words, A minus B is a multiple of 3. Okay. Here's an example. Here are some examples. So 1 is related to 1 because 1 minus 1 is 0, which is 3 times 0, right? So it's a multiple of 3. And 1 is related to 4 because 1 minus 4 is negative 3, which is 3 times negative 1. It's a multiple of 3. And 2 is related to 5, because 2 minus 5 is negative 3, and so on. And also 9 is related to 3, because 9 minus 3 is 6, which is 3 times 2. So they are all multiples of 3. So now we try to show that this relation is indeed an equivalence relation. Okay, so first we need to prove the reflexivity. For any integers, we have a minus a is equal to 3 times 0, right? Therefore, a is related to a. And 2, if a is related to b, then a minus b is a multiple of multiple of 3, okay, for some integer, okay, and this means b minus a is a multiple of 3. It's a 3 times negative m, right? So this means b is related to a. Therefore, a related to b implies b related to a, so this relation is symmetric. And what about transitivity? Suppose a is related to b and b is related to c. Then this means a minus b is a multiple of 3, let's say. And b minus c is a multiple of 3, let's say, times n, and m and n are integers. Okay? Then, let's see, a minus c. A minus c is a minus b plus b, a minus b plus b minus c. Okay, which is 3m plus 3n. So we factorize, and of course m plus n is an integer. Therefore, a is related to c. So it's transitive. Therefore, this relation defined by this is an equivalence relation. So in this particular case, we say a is congruent to b. A and b are congruent. Okay, so why an equivalence relation is important? Because that gives us a way to classify the elements of a certain set. Okay, but what do we mean exactly by classification? So here's one possible way to define it, which we term partition of a set. Partition of a set. Okay, so let S be a set. Then a partition of S is a collection of subsets of S. S such that with the following properties. 1, if X is an element of C, so that is X is a is a subset of S, then X is not empty. Okay. And 2, if X and Y are elements of C and X is not equal to Y, then they are disjoint. X and Y are disjoint, meaning their intersection is the empty set. Okay. And 3, the union of all elements of the partition is S, meaning the union of X, which is X's are elements of C, so we take the union of all these C, and then it is equal to S itself. Okay, so this may be a little bit confusing. So let us write this collection of subsets of C as this: x1, x2, up to maybe xn. Okay? Now it may be countable or may be uncountable. Let's say it's countable. So each of these x1, x2, up to xn, they are subsets of they are a subset of S. Okay, so x1 is a subset of S, x2 is a subset of S, and so on. Okay, then what this means is x1 union x2 union, and you take the union of all of these subsets, then that is equal to S. So this is what this means. Okay, so each element of C, you name it as X, then take the union of these, then it is S. So what this means is that each of these subsets is not empty. Okay, then the second condition says none of these overlap with other elements. And the third condition means collectively they cover the entire set S. Okay. So we say this property as mutually disjoint. And we say this property as collectively exhaustive. So collectively means together, and exhaustive means they cover the entire S. Okay. So this is a way to view what classification means. Okay. So classification means we classify each element of S into one of these subsets, x1, x2, up to xn. So that is classification. Okay, maybe we can explain this more visually. So suppose we have this set S. So this collection of subsets of S is something like this. So this is just one of these, like x1, x2, x3, x4, and so on. So each of these subsets, they don't overlap, but together they cover the entire S. So this is a way to view this notion of partition. So classification means we pick any element of this S and associate with one of the classes, one of these subset. So that's classification or partition of the set S. So how does the notion of partition relate to equivalence relations. Here's how. We define something called equivalence classes. In short, each equivalence relation generates a set of subsets of S on which the equivalence relation is defined. So let's say we have an equivalence relation. So it's not just a relation, it's an equivalence relation. Equivalence relation on a set S. Okay? Then for each element of S, we define this subset of S called bracket X. So for each element X of S, we define bracket X, which is a subset of S such that each element of this subset is equivalent to X. Okay? So this is a subset of S, obviously. And this subset is called the equivalence class of X, or equivalence class containing X. Equivalence class containing X. So basically, this is a subset of S that contains all the elements of S that are equivalent to X. Okay. And for each element, we can define this subset. But some of these subsets are equal to each other. Okay. But anyway, we can have a collection of these subsets. We have a collection of equivalence classes, which we write as S divided by the relation. So this is the collection of all equivalence classes. All equivalence classes. And this is also called, so this collection of all equivalence classes is called the quotient set. Quotient set of S by tilde, this relation. Okay. So this is the definition of equivalence classes, and we also define the quotient set of S by the relation. Okay, let's see some example. Again, consider this equivalence relation on integers where A is equivalent or congruent to B if A minus B is a multiple of 3, where this M is an integer. If, actually it's if and only if, okay? So we have seen that this relation is an equivalence class. So no, this is an equivalence relation. So for example, equivalence class of 0. What is it? So it is a set consisting of all integers such that that is equivalent to 0, right? So what is equivalent to 0? So that means y minus 0 is a multiple of 3, right? Multiple of something. 3 times something. So this means that is 0, 3, 6, 9, actually it's plus minus 3, plus minus 6, and so on. So it's all the multiples of 3. That is the equivalence class of 0. What about equivalence class of 1? So by definition, this is the set of all integers that are congruent to 1. So that means this. That is 1, 4, what is it, 7, and so on. Of course, there are negative numbers also. That would be, let's see, negative 2, negative, what is it, negative, it's negative 2, negative 5, let's see, negative 5 is that so? 1 is negative 6, yeah, that is, so negative 5, and negative 8, and so on. What about the equivalence class of 2? That would be 2, 5, 8, and so on. And also negative numbers like negative 1, negative 4, negative 7, and so on. What about the equivalence class of 3? That is 0, and 3, 6, 9, and so on. And of course, it's plus minus 3, plus minus 6, plus minus 9, and so on. So actually, this equivalence class is the same as this equivalence class. So if you try equivalence class of 4, 5, and so on, you see that we actually have only 3 distinct equivalence classes in this case. That is equivalence class of 0, equivalence class of 1, and equivalence class of 2. So therefore we have this quotient set Z over congruence is made of these 3 sets, these 3 subsets of integers. So that is 0 plus minus 3 plus minus 6 and so on, and 1, 4, 7 and so on, and 2, 5, 8 and so on. Actually, that is, to make it more precise, we have 3k, where k is integers. So it's a multiple of 3, and multiple of 3 plus 1, and 3 times integer plus 2. So these 3 subsets collectively cover the entire integers. So if you take the union of these 3 subsets, then that is equal to the set of all integers, and any of these subsets do not overlap with other subsets, right? This subset has no common elements with other subsets, and so on. Therefore, you can see that this quotient set is a partition. Partition of integers. Okay, so we have this observation, at least for the set of integers. Okay, now based on this observation, we prove a more general result. Okay, so here's a proposition. Let tilde be an equivalence relation. It's not just a relation, it's an equivalence relation shown on set S. Then this quotient set of S by this relation tilde is a partition of S. Okay, so let's prove this. To prove this, something is a partition. We show that this collection of subsets of S satisfies the three properties, defining properties of a partition. Okay, so here's the proof. First, we need to prove that each element of this quotient set is non-empty. Okay, so for any element of S, then for any element of X, because this tilde is an equivalence relation, it is reflexive. So X is equivalent to X. That means X belongs to the equivalence class of X itself, of course. Therefore, this equivalence class is not empty. Okay, so this proves the first property. Second property is the mutual disjointness. Okay, so that means if bracket y is not equal to bracket z, then their intersection is empty, right? We want to prove this. Okay, but proving this directly is not so easy. We want to prove this. So instead, we prove the contrapositive. Okay, contrapositive of this statement. As we have learned in the propositional logic, the contrapositive statement proposition is equivalent to the original proposition. So the contrapositive of this is negation of this implies the negation of this. So that means if y bracket intersect z bracket is not empty, then y bracket is equal to z bracket. So this, we need to prove this. Okay, so let's see. So now we assume this intersection is not empty. Okay. Then, since it's not empty, there is some element in this intersection, right? So let's say X belongs to this intersection. Okay, so there is an X in this intersection. Since, okay, we suppose this. Suppose this. Then there is at least one element X that belongs to this intersection. Okay, then this means X is equivalent to Y and X is equivalent to Z. Right? So that means by transitivity, and actually, so by symmetry, this means y is equivalent to x. So now y is equivalent to x and x is equivalent to z. By transitivity, that means y is equivalent to z in this case. Okay, so that means for any element in bracket y, we have a is equivalent to y, which is y is equivalent to z. Therefore, a is equivalent to z. That means a belongs to bracket z. Okay, this means y is a subset of z. Bracket y is a subset of bracket z. Okay, and in a similar manner, for all element a in bracket z, we have, we can just go in a reverse direction, and for any element of z bracket, we can show that a belongs to bracket y. So this means bracket z is a subset of bracket y. So since we have this and this means bracket y is actually equal to bracket z. That is what we wanted to prove, right? Let's see, where is it? This one. Okay. That means by taking the contrapositive of this, we prove we can see that this original statement is true. So if bracket y is not equal to bracket z, then their intersection is empty. Okay. And lastly, we need to prove that the quotient set is collectively exhaustive. So for any element of S, we have x is equivalent to x because of reflexivity. This means x belongs to bracket x, which is an element of S over tilde. So this means every element of S belongs to precisely one of the elements of the quotient set. So that means every entire S is covered by the elements of this quotient set. Therefore, S over tilde is collectively exhaustive. So this proves everything we wanted to prove. Therefore, S over tilde is a partition of S. So that is the proof. So by introducing an equivalence relation, we can classify all the elements of the set without exception and without redundancy, without overlap. So that's what's nice about equivalence relations.